Welcome back students to this week's and modules lecture. So, in the last two lectures we have gone through, looked at the basic fluid properties, then we derived the rate of shear strain, and this is an important property which we are going to use in our further analysis. So, we are going to this is the last point where we concluded written the extensional and the shear strain rates. Extensional is epsilon xx, epsilon yy and epsilon zz, whereas the shear strain rates are epsilon xy, epsilon xz and epsilon zy. So, this is the matrix of the strain rates, and the values of epsilon xx, epsilon yy and epsilon zz we had already defined, we had already derived that epsilon xx was del u by del x, okay, and similarly epsilon yy was del v del y and epsilon zz was del w del z. So, after that we are going to start the classification of fundamental equations. Sorry. Classification of fundamental equations. Okay. So, actually there are three laws of conservation of physical systems. The first one is conservation of mass. This you have already seen, that is continuity equation. The second one is the second conservation equation is conservation of momentum. And this is analogous to Newton's second law. The third is conservation of energy, and this has something to do with first law of thermodynamics. All right. So, the three unknowns that must be obtained simultaneously from above three basic equations are velocity, second is pressure. So, writing V pressure, which is thermodynamic, by P, and T as temperature, absolute temperature given by T. All right. So, we actually consider two independent. So, when it comes to thermodynamic variables, we consider two independent thermodynamic variables. Which are actually pressure and temperature. Okay. However, the final form of conservation equations also contains four other thermodynamic variables. And what are those variables? We are going to write it down. One is rho, also called density. Second is H, that is enthalpy. There is mu, viscosity, and K, thermal conductivity. All right. So, we go to the next page. So, we assume something, and that assumption is that we assume that there is a thermodynamic equilibrium. So, under the assumption of thermodynamic equilibrium, rho as a function of pressure and temperature, H is also a function of pressure and temperature. So, mu is equal to, mu is also a function of pressure and temperature, and K, that is the thermal conductivity, K is also the. So, basically all these dependent variable are a function of pressure and temperature under thermodynamic equilibrium. All right. These values, so which values? These values, rho, H, mu and K, these values are generally in form of tables, charts, or some theoretical theoretical formula. Usually in hydraulics, for our purposes, rho mu k are assumed constant and H is proportional to temperature. So, in this particular course we are going to deal mainly with rho and mu, which will be considered constant. All right. So, the discussions above, so the above consideration applies to a fluid of uniform homogeneous composition, which means diffusion and chemical reactions are not considered. Okay. All right. So, with this background in mind, we will get started with our first equation. So, our first equation is conservation of mass, or also called equation of continuity. All right. So, actually all the three laws for the derivation require the particle derivative or a substantial derivative or the material derivative, which we have already seen in our previous lectures. So, I will take you to that where we wrote the material derivative. So, here, so material derivative of any quantity is written as dq dt as del q del t plus u del q del x plus v del q del y plus w del q del z. So, this is the material derivative. So, we going back to the three laws, including this one, the three laws of conservation utilize the particle substantial derivatives. Okay. So, that is d dt is equal to del del t plus. Okay. So, this is what we utilize. Actually, in this particular course we are going to deal with only conservation of mass and conservation of momentum. The third equation, the first law, the first law of thermodynamics, the conservation of energy, is outside the scope. So, we are not going to deal with that in this particular course, but for the people who study mechanical engineering, that law is also very much applicable. So, writing now law of conservation of mass. Okay, so what does this law says? Law of conservation of mass. We said that this particular equation will be used for the derivation of this equation of continuity. So the law of conservation of mass says that mass is equal to rho, and this is V. I am writing a different V because we mostly say in hydraulics V as velocity. So this is constant, right? So that is conservation of mass. All right. So this equation we call 1 for now, and this equation we will call equation number 2. All right. So if we put equation number 2 in equation number 1, this becomes del d m is equal to is equal to 0 is equal to, by chain rule, rho all right. Now this, you see there are two terms on the right hand side, rho dv dt plus v d rho dt, where v is the volume. Okay, so actually the rate of change of volume, so the total change in volume, so dv dt can be related to the fluid velocity. How? If we notice that the normal strain rate is equal to rate of volume increase of a particle per unit volume. Okay, so the normal strain rate actually is equal to the rate of volume increase of a particle per unit volume. All right. So we go to another page. All right. That means epsilon xx plus epsilon yy plus epsilon zz is equal to, this is the definition, 1 by v dv dt. All right. So we also know that this is equal to, from our previous lectures derivation, epsilon xx was del u del x, epsilon yy was del v del y, and this was epsilon zz was del w del z. This was what we actually had derived. All right. And this actually is nothing but divergence of v, or this, so this is a velocity, right, because it is u v w. All right, and this equation we call equation number 4. Combining equations 1 to 4 to eliminate this volume, what we can get? We will get, so we are going to get d rho dt plus rho divergence of v. So this is velocity v, not the volume v, is equal to 0, or all right. So this is equation number 5. All right. If we assume incompressible flow, then reduces to divergence of v is equal to 0. All right, and this is nothing but equation of continuity. All right. Very good. So what we have done is we have been able to derive the equation of continuity. So and this is equation number 6. So we look at a related concept called a stream function now. What is a stream function? If the continuity equation reduces to only two non-zero terms, then it can be satisfied identically. And replaced by so-called stream function, which is given by psi. Okay. So continuity equation in 2D, let's call it xy plane, 2D steady compressible flow is written as, so if I steady, that means there is not going to be any del t term, right? So we will have only del x because it is compressible, del y of rho v is equal to 0, right? This is equation number 7. All right. If we define the stream function psi such that rho u is del psi by del y and rho v is minus del psi by del x. So, we have written the continuity equation in 2 dimension, and if we are defining a function which we will call stream function such that it satisfies rho u is equal to del psi by del y and rho v as del psi by minus del psi by del x, then if we substitute equation 8 in equation 7, we observe we see that equation number 7 is satisfied identically. Of course, the condition here is if phi is continuous to second order derivatives. Before we conclude, I would like to just look at it. Okay, how? So, del x rho u, how is it satisfied identically? So, rho u is del psi del x, so it will be del x of plus del y of rho v is minus del psi del x. Okay. So, this means LHS and RHS was okay. So, I think this is right time to finish today's lecture, and we start from where we start in the next lecture from where we have just stopped, and thank you for listening. I will see you in the next lecture.